partial derivatives. Let us look at a brief synopsis about what can be learnt in partial derivatives. Basically, if z is a function of x and y, dou z by dou x and dou z by dou y, these are first order partial derivatives. Dou square z by dou x squared, dou square z by dou y squared, dou square z by dou x dou y, dou square z by dou y squared are second order partial derivatives. The next point is dou z by dou x, dou z by dou y. If you make a vector out of this vector is known as the gradient vector. Then we can make a matrix dou square z by dou x squared, dou square z by dou x dou y, dou square z by dou x dou y, dou square z by dou y squared, which is called the Hessian matrix. Then we can have dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y, given the transformations u is equal to f of xy and v is equal to g of xy. Then when it comes to the problems of optimization, optimization is the process of finding out maxima minima of functions of several variables. And suppose you have a function f of xy and we want to find its maximum or minimum values, I mean in the local sense, then you first solve dou f by dou x is equal to 0, dou f by dou y is equal to 0, and by solving this you get what are known as critical points. You get the critical points. Critical points are points where the function attains relative maximum or relative minimum. Now, once the critical points are obtained, you substitute the critical points in the Hessian matrix H, which has already been defined here. Now here, there are three possibilities. Possibility 1, you will get a local minimum if H is positive definite. So when H is a positive definite matrix, then that critical point is going to return a local minimum. You will get a local maximum if H is negative definite. And finally, you get a saddle point if H is indefinite. So there are three possible scenarios with respect to function optimization. Of course, when there are no constraints. When there are constraints, you use the Lagrange's multiplier method, which is altogether slightly different technique. But these are the basic points in partial derivatives that one must remember. The first thing is trying to understand the first order derivatives and the second order derivatives. However, there is one small correction here. This is dou square z by dou x, dou y dou x. So we have dou square z by dou x squared, dou square z by dou y squared, and two cross polar derivatives. But generally these two are equal under certain conditions. Then this is called the gradient vector. This is the Hessian matrix. This is Jacobian matrix. And these are the rules for function optimization.